Okay, Sam, I think you can go ahead and start.
Okay. Well, yeah. Hello, everyone. Welcome to the March 2024 edition of VAST. It's the Virtual Astronomy Software Talks seminar, where today we have two great speakers, Nils Vu and Nick Roberts, who are going to talk about elliptic solvers in their respective codes, which are SpECTRE and Poseidon. Just a reminder to everyone that we have so this month is elliptic solvers. Next month we have one talk scheduled by Rich Townsend about multidimensional stellar grids, and we are always open to talk proposals. So if you have something you'd like to present, then please navigate to the VAST GitHub page and submit an issue. And we always encourage talks from early career researchers. So if you or maybe one of your students or colleagues has something that they would like to present, then I would encourage them to do so. As you'll see, it's a very low, what's the word? Very informal kind of talk, but you get some exposure and you get some experience giving talks, and you might make some new connections. So, yeah.
And Sam, if I could just add, especially if you can talk next month.
Yeah. Yes, the sooner the better. Yeah. Okay. And I think that was everything. So what is this? Oh, yeah. So if you just joined, these talks are recorded. So if you don't want your face to appear on YouTube, then feel free to turn off your camera. That's fine. And if you have questions during the talks, then put them in the comments. And each talk will be 20 minutes. And after each talk, we'll answer maybe one or two questions. And then after the second talk, we'll have the remainder of the hour for open discussion, where hopefully all of the remaining questions will be answered. Yes. So with that said, sorry, yeah, like I said, our speakers are Nils L from Caltech, and he's going to talk about SpECTRE. And then after that will be Nick Roberts from the University of Tennessee at Knoxville, who will talk about Poseidon. And just a disclaimer that I do work with Nick, but he went through all the official channels to submit a talk and get approved by the committee, who is much more than just me. So yeah, all of that. And yeah, so I guess we'll start with Nils, if that's okay.
Sure, I can start.
Okay, so if you go ahead and share your screen, and the floor is yours.
Give me a second here. Right. So can you see this okay?
Yes, looks good.
Okay, cool. So yeah, hi everyone. My name is Nils Vu. I'm a postdoc at Caltech here, and I'm working on numerical relativity. And yeah, so I'd say I'm a computational physicist working between gravitational physics and high performance computing. And so specifically, I work on these simulations of merging black holes and neutron stars. And you see two of these black holes on the screen here. And yeah, in the spirit of this seminar, I thought today I'll talk about in equal parts black holes and about software. And so I talk about how we represent these black holes as elliptic partial differential equations, and then how we solve these elliptic PDEs with this whole stack of numerical technologies on supercomputers. And I'll mostly talk about this numerical relativity code SpECTRE that I link at the bottom right here. And also, if you want, you can already pull this Docker container here if you want to try some things out, some things later, and if you have Docker installed on your laptop and so on. I'll have this link on another slide later as well. Okay, so just for context, this is what we do in numerical relativity. Okay, so what you see here in this movie, this is one of our simulations of an orbiting black hole binary. And then these black spheres, they are the apparent horizons of the black holes. And they are always guaranteed to lie within the event horizons of the black holes. But they can actually be found at every time step, which makes them useful for numerical simulations. And then the black hole in the middle, that's about three times or so more massive than this smaller one orbiting it. And it also spins, and you'll actually see some precession in the orbital plane right now. And then what you see in colors, that's the gravitational radiation that these orbiting black holes emit. And you can also see this as a waveform here at the very bottom. And so, yeah, these black holes are radiating away energy in gravitational waves. And so their orbit is shrinking. They start to move even faster, radiate more energy. And then you see these two black holes in this panel on the right here. They move ever closer together. The orbital plane is precessing. And they emit ever stronger gravitational radiation. And then they come so close that they merge. And so they form a common apparent horizon that encloses the two individual horizons. And then they ring down as the single black hole emitting this one last burst of energy. Okay, so in numerical relativity, we simulate these strong gravity scenarios, right? Like these black hole mergers, also neutron star mergers, supernovae, accretion disks, etc. And we extract their gravitational waves. And so, and then of course our predictions of these gravitational wave signals are essential to analyze data from gravitational wave detectors like LIGO here. And this on the right here, this is actually the first ever gravitational wave signal that was measured in September 2015, and it actually matched our predictions from a black hole binary merger perfectly. And this gives us so much confidence that we have actually measured a signal from two merging black holes here in 2015 and many times since then. And so this is why to do this, we have to evolve the Einstein equations numerically. And you probably know that the Einstein equations are the set of horribly nonlinear coupled partial differential equations. And this is why our simulations get very expensive very quickly, and they can easily take weeks to months. And people have run this for a year or more. And that's where our focus on efficient computational methods for solving PDEs comes from. Okay, and so I specifically work with the SXS collaboration and about 15 people or so on this next generation numerical relativity code called SpECTRE. This is the successor to a code called SpEC, the spectral Einstein code. This has been very successful in this business, producing very high accurate waveforms, but it's limited in its parallelization. It can run on maybe 50 or 60 cores or so. And so we are building this new code, SpECTRE, as our sort of next generation code to run on large petascale and future exascale computers. And we focus here with SpECTRE, we focus on high order discretization methods and on parallelization. So we use these discontinuous Galerkin methods to retain this high order spectral exponential convergence that made our old code so strong. And we couple it with a task-based parallelism to scale to large computers. And then, some details. The code is written in C++ 17 and 20 for the performance critical parts. And then the tooling around is written in Python. And we're building this on this Charm++ task-based parallelism framework. It uses API as a backend to communicate data between nodes. And then we also use an OpenMP for shared memory parallelization of some auxiliary tasks. The code is open source. It's publicly available at this GitHub repository that I link here. And we have extensive unit testing suites. We have continuous integration based on GitHub Actions. We do monthly containerized releases. So if you have Docker installed on your laptop, or if you have something like Aptainer, formerly Singularity, available on a cluster that you have access to, you can actually try to pull this container and try it out in a few slides, and actually run a quick simulation of black holes yourself. Maybe not for months. And then all this technology is actually really important to us to encourage reproducible science. So both so we are confident in our scientific results, and also so others can verify them. And also, of course, so our code remains maintainable in the future for the science we want to do. Okay, so but what does this code do, right? So in numerical relativity, we use this 3+1 decomposition of GR, of general relativity, to foliate this 4-dimensional space-time into spatial hypersurfaces. So the idea is to have this Cauchy problem where we start with initial data on an initial hypersurface, and then we evolve it forward in time to trace out the entire spacetime. And of course, this evolution part of the code is difficult enough, and lots of people in our collaboration are working on that. But before we can even start a simulation, we always have to solve this constraint sector of the Einstein equations for initial data. And that's what I'm focusing on here, on this initial data part that we always start with. So for example, this is the slice of spacetime, a 3D slice of 4-dimensional spacetime, right? It has two black holes, some masses and spins, they orbit each other. And to generate this slice of spacetime, we have to solve an elliptic boundary value problem. And in this case, this is the Einstein constraint equations. It's a set of 5 coupled nonlinear elliptic PDEs. It's the XCTS system for those who are familiar with this. And then in this formulation, black holes are actually represented only by boundary conditions. So we excise these two regions from the computational domain, and we impose boundary conditions that represent black holes with some masses and some spins. And then solving these elliptic equations it's like an entirely spatial problem, right? Where you need to find the solution to these equations numerically everywhere at once on this slice, respecting these boundary conditions. And so this requires very different methods than the time evolution part of the code. And that's where the elliptic solver comes in. So solving elliptic equations is essentially a matrix inversion problem. So in a nutshell, it always involves these two steps. So first, we discretize the equations on the computational grid, so they become a matrix equation over grid points. And then second, we just have to invert this giant matrix to get a solution at every grid point. And so just for reference, we can easily have millions of grid points, right? So these matrices are pretty big. And so we never actually build them explicitly. Because, we use many different methods for both of these steps. And the key in SpECTRE is to make all of this very parallelizable. So for the discretization method, I developed this discontinuous Galerkin scheme that essentially it splits the problem into many sparsely coupled sub-problems that you can sort of see in this block diagonal form of this matrix representation on the right here. And then for the inversion, I developed this iterative method that makes use of this structure to parallelize to computing clusters. And then together, this is the initial data solver of our code. And so it sits at the start of every simulation of merging black holes that we do. So the job of this elliptic solver is essentially to invert giant matrices on supercomputers, right? And so we use this whole stack of iterative methods to do this effectively. So we handle the nonlinear part of the Einstein equations with a standard Newton-Raphson algorithm with a line search. And then in each step of the Newton-Raphson, we solve the linearized problem with a Krylov subspace iterative algorithm, such as GMRAS or conjugate gradients. But these algorithms struggle, as is well known, to solve for large-scale modes in the solution that span the entire computational domain. And they also parallelize very poorly. So we run a multi-grid preconditioner at every iteration of the Krylov solver. It interpolates the problem to Corsair grids, where then these large-scale modes, they become small-scale. We use the solutions on these Corsair grids to correct the finer grids. It's a standard multi-grid scheme. And then to actually, and now this is where it becomes non-standard, to actually solve this problem approximately on every level of this multi-grid hierarchy, we use an additive Schwarz smoother, which restricts this problem to many overlapping subdomains and then solves them all in parallel and combines the solutions by weighting these the overlap regions. And then each little subdomain is actually solved in serial using another Krylov subspace solver, such as GMRAS, conjugate gradients. And this Schwarz subdomain solver, this is the main source of parallelization in this algorithm, because all these little subdomain solves are independent of each other and they can run on different cores. And then finally, each subdomain solver is supported by more preconditioners, so it converges faster. So it's preconditioners here. So we can use here any analytic or partially computed or cached result to approximately invert the subdomain problem to make it faster. And so currently we precondition the subdomains by approximating every tensor component of every equation with the flat space Laplace operator which we actually build explicitly on the subdomain, invert within incomplete LU decomposition, and then cache for the entire duration of the storm. So yeah, lots of nested preconditioners that work together, multi-grid to resolve large-scale modes, Schwarz smoother to enable the parallelization, and subdomain preconditioners to speed up the subdomain solves. That's the SpECTRE elliptic solver. Okay, so I'll finish with some results. First, just looking at a single Schwarzschild black hole on a spherical domain like this with an excised horizon. I want to point out that this strategy achieves scale independence. So you can see this in this plot with on the right with the number of Krylov iterations over the refinement level. So from left to right, we split the spherical shell, the spherical domain, into more and smaller elements from 6 on the left to over 200,000 elements at the very right in this plot. And then just look at the solid line at the bottom. It shows that with the multi-grid Schwarz preconditioner, the number of Krylov iterations actually stays constant with increasing resolution. And instead of increasing the number of iterations here, the additional computational work that's needed at higher resolution is pushed into more multi-grid levels with more subdomain problems. And that's good because those can actually be parallelized. And then to look at the parallelization, let's actually look at this binary black hole initial data solve. So here's this domain that we're currently using. This is cut through the orbital plane in 3 dimensions. And you see the grid is shifted a little to accommodate the mass ratio of the black holes, that one is bigger than the other. And these 2 excision surfaces in the center, they are actually deformed to ellipsoids to conform to spinning Kerr horizons. The black lines, they are the element boundaries that can run on different processors. And the light gray, those are grid points. And since this is a vacuum problem that is smooth, we should get exponential convergence by increasing the number of grid points per element in this discontinuous Galerkin scheme. And this you can see actually on this left plot here. So this actually shows the discretization error of the solution over the total number of grid points per dimension. And then the gray line, that's our old code spec. It always uses 11 big spectral subdomains for the initial data, written 20 years ago. And the black line, that's SpECTRE on the domain that I just showed you, a similar one. And you can already see this. The black line is a little further right than the gray. So SpECTRE needs a few more grid points to reach the same resolution than SpEC. Because we split this domain into so many small DG elements. But then on the right here, you see the wall time for one of these configurations over the number of compute costs used to solve it. So this is a strong scaling plot. And you see that SpEC's initial data solver can't really scale to more than 11 cores. But with SpECTRE, we can then scale this configuration to about 120 cores in this case. And this already makes this about 10 times faster than SpEC. And because of the scale invariances I just showed you, we can always split this domain into more elements, scale it up to more cores to solve harder problems. All right, so that's the SpECTRE elliptic solver for you. And this is my second to last slide. So since this solver uses grid points so efficiently with these spectral DG methods, you can actually try running it on your laptop now if you want. You can grab an interactive node on your favorite supercomputer to try it. Maybe do it after the session, so you don't do it during the next talk. So I told you that we publish containerized releases, right? So if you have Docker or something like Aptana, which is formerly Singularity installed, you can generate some black holes on your computer right now. Just run this container or on the cluster, if you have an Aptana module installed, you can use that. You give it some parameters. Q is the mass ratio, D is the separation between the black holes, W is omega, it's the orbital angular velocity, and then A is the radial velocity, and an output directory. And then this will solve the Einstein constraints for you. It will give you a slice of space-time with 2 black holes in it. And this will take a couple of minutes, maybe more, depending on the number of cores that you have available. It will actually use all of your cores by default, so don't run it on the login node of your cluster for the sake of your colleagues. And yeah, when it's done, you can also use some of the plotting tools that we provide on this container to quickly interpolate this data to a slice, and then you get this plot on the right here that shows one of these space-time variables around the two black holes. And yeah, so I'll just conclude here. I've shown you how we generate binary black hole initial data for our simulations and how we can make it an order of magnitude faster than our old code by focusing on parallelization and on higher order DG methods. Here's the name of the container again, where we publish, where I just pushed the Docker container to. We're also working on initial data for other systems that are not quite public yet. But one thing that I wanted to highlight is a grad student who's working with us, PJ Nee at AEI Potsdam in Germany, has made very impressive progress with this initial data for black holes in scalar Gauss-Bonnet gravity, which is an extension of GR with a scalar field that couples non-minimally to the gravity sector. So we're able to generate initial data where this Gauss-Bonnet scalar is quasi-stationary on a binary black hole background. And here's an example here on the top right, is an example of this data with two scalarized black holes with opposite scalar charge. And so we're happy to share this data on a request, and we'll also make this public soon. And then at the bottom is another example. It's an interdisciplinary application where we simulate the thermal noise in thin mirror coatings induced by a laser incident at the top. And this is actually an important problem in the design of gravitational wave detectors. And it turns out that this is described by a set of elliptic PDEs as well. And we're actually pretty good at solving those. So even though this problem has nothing to do with numerical relativity, we've approached this with our code. Yeah, so SpECTRE has this high performance solver for generic elliptic PDEs. And you can find more information in this paper or on our website or on GitHub. Okay, thank you.
Great, thanks, Nils. That was a great talk.
Oh, I already see a question by Michael.
Yeah. So yeah, if you can read, can you go ahead and answer that?
How good am I finding the C++20 support in different compilers like CUDA? We actually have switched to C++20, and we are using some mostly templating features from C++20. But we are not expecting to be able to fully use C++20 for another maybe 5 years or so, because we need a compiler support propagate to supercomputers, right, which is always super slow. We have considered running more containerized, running the code actually containerized on supercomputers, so we can use our whichever compilers we want. So we might actually do that to get more C++20 support. I haven't tried the CUDA support in Clang yet, but I want to. That sounds really useful. And I want. Oh right, the thing that I'm mostly excited about for C++20 is getting rid of includes. And so yeah, I think maybe that could actually make it worth just bundling our own compiler in containers and running our simulations containerized. Yeah.
Yeah.
Great. Thank you. Okay. So I have more questions than others may, but we'll save them for the open discussion section.
Sure. Yeah.
Yeah. So thank you again, Nils. Appreciate it. Also, thank you for getting up so early for this. So next, Nick Roberts will talk about his elliptic solver Poseidon, and just a statement out there that he's on the job market. So if you are interested in someone who is expert in elliptic solvers, then keep your eyes out for his application. And with that, yeah, if you want to go ahead and share, Nick, and the floor is yours.
There we go. Hello, everybody. Thanks for having me here. So I'm going to talk to you today about my code Poseidon. I'm a grad student at the University of Tennessee. I work with Sam and the Tornado crew. So let's see. Come on. There we go. So what is Poseidon? Poseidon is a relativistic gravity solver that I've been developing for the past couple of years. It's based on the extended conformally flat formalism of general relativity, which I'll talk a bit more about in a minute. It solves the XCFC metric and hands that back to whatever, code is calling it. It's been built with distributed memory parallelization, so it's good to run on the larger computers. It's compatible with AMRX data types. So if you're running with adaptive mesh refinement, it's good to go. It can handle that. It is built in Fortran. I know a lot of people like C and C++, but we're old school with Fortran here. There's the GitHub. I keep it there. I have continuous integration set up, so I try to make sure that it's always good to go if anyone ever needs it. Primarily, it's used with the toolkit for high order neutrino radiation framework, Tornado. I know Sam has discussed it. I think it was last October. It's a really neat code. We do a lot of fun work with blowing up stars. So yeah, definitely look into both of these codes if you've got the time. So before I really get into what Poseidon does, I'm just going to give, a little brief background, to set up the problem that it's actually solving. So in GR, you have the metric, which is, the mathematical object that measures the curvature of space-time. And that's what Poseidon solves for. You need the metric for, if you're doing hydrodynamics, neutrinos, anything with GR, you need the metric to know how space-time is doing. We adopt the 3+ formalism, the same as Nils in the last presentation. Over here on the right, you kind of have the standard diagram. You have, a lapse function that measures the time between adjacent time slices. You have the shift vector, this beta, that measures how a point on a time slice is moving as it goes to the next. And then on these time slices, you'll have a spatial 3 metric. And all of that information comes together to form your full 4-dimensional space-time metric. Now, this metric is governed by, the Einstein field equations, which, in this form are nice and compact and almost look deceptively cute. But as soon as you start opening them up, they become very complicated. Those terms explode and it just gets hairy. So to make life better, we make approximations. And that's where the extended conformally flat condition comes in. It's an approximation on full general relativity that, it places some restrictions on it, simplifies it down, and makes the equations a lot easier to handle. So the extended conformally flat condition places 2 main restrictions on general relativity. The first is it requires that spatial 3 metric on the hypersurfaces to be conformally flat. So you lose a lot of degrees of freedom right there, simplifying your equations. Secondly, it requires the extrinsic curvature tensor to be 0 for all time. Now, the extrinsic curvature tensor measures how that spatial hypersurface is embedded in the larger 4-dimensional space-time manifold. So by restricting this, you restrict how those space hypersurfaces can evolve through time. Lastly, and this is where the extended portion of XCFC comes in, is this last, didn't mean to jump ahead there. This last approximation here on the extrinsic curvature tensor. It's expanded and they drop this transverse traceless portion of the extrinsic curvature tensor, again, dropping degrees of freedom. It's these last two, it's this restriction on K here that actually kills out a lot of the gravitational wave degrees of freedom. So in XCFC, you have no gravitational waves, but you can recover them in post-processing. So it is still a valid method going forward with, realistic simulations of core collapse supernovas. So given all of these restrictions, the Einstein field equations get reduced to this set of 4 elliptic equations here. And this is what Poseidon is actually aiming to solve. You have, an equation for your conformal factor and your lapse function and the shift vector. Those are your, your metric variables. Introduced by the approximation, you also have this x vector. It's just called the x vector. And it helps, it goes into the computation of these approximate extrinsic curvature tensor terms, these A hats. So this is what Poseidon solves. This is the system we have to handle. And so let's look at it. There are a couple of, notable features. The first thing is that there are two, types of equations that we've got to solve. The first is this vector Laplacian with kind of, a modification term here. The second are scalar Laplacians, your good old-fashioned scalar Laplacian. So we have two different systems to solve. And on top of that, if you look, the vector Laplacians are linear. They have no dependence on, the variables in question. But the scalar Laplacians are nonlinear. So not only do we have two types of systems that have to be discretized and solved, but we also have linear and nonlinear systems. So that's a challenge that has to be, faced. But there is, a silver lining, and that silver lining is that these equations can be solved sequentially. The x equation up here at the top has no dependence on the other metric variable, so you can solve it in isolation. Use x to calculate your A hats, and then you can solve for the conformal factor. Once you have that, you have enough information to solve your lapse function equation. And once that's done, you're on to your shift. And once you're there, you've got your system solved and you're good to go. So that's really nice about the XCFC formalism, is it breaks up these equations so that they can be solved sequentially. In a similar formulation to CFC, you don't have the x equation, but you have all three of these equations down here for the metric variables are all coupled. So this is a really nice advantage that you can break the system down and handle them piece by piece rather than all at once. So let's get on to how Poseidon actually, attacks these equations. Because Poseidon is designed to be primarily run with core collapse supernova simulations via Tornado, it's specified on a spherical polar domain. It doesn't have the freedom to use Cartesian. It's always on spherical polar. On this domain, we use a combination of Galerkin projections to discretize the equations. If you're not familiar with Galerkin projections, the basic idea is you take your solution and approximate it by a sum of coefficients and basis functions. And to specify these coefficients, you require that the residual of your problem is orthogonal to another set of basis functions. In general, these two sets of basis functions don't have to be the same, but for Poseidon, we've chosen them to be the same. The test and the trial functions are the same. And we put it through this process and we arrive at discretized equations that are solvable. Poseidon uses a combination of real spherical harmonics in the angular dimension and finite element polynomials in the radial dimension to discretize these equations. So let's look briefly at these basis functions because they're the heart of the method. The basis functions you choose to represent your solution are, the heart of this method. So in the angular dimension, we use real spherical harmonics. These are related to the standard familiar complex spherical harmonics by this relationship here at the top. You see, they're basically just products of them, and taking the products of two a spherical harmonic and its complex conjugate denoted by the star, you eliminate the complex portion of these values, but you retain all of the original properties of the complex functions, among which are useful for the discretization are the orthogonality of the real spherical harmonics, and that they're eigenvalues of the Laplace operator. That's why we use the spherical harmonics, because we're dealing with Laplace, Laplace operator dominant equations. So this simplifies the discretization immensely. Other benefits of using real spherical harmonics over the complex cousins They're real valued, so you don't have to, you're not storing two reals, you're only storing one, which, it's a savings in memory and computational expense. Further, you only need to store the positive M values of, like, this PLM is the associated Legendre polynomial. With the complex spherical harmonics, you need the full range minus M to plus M. With these, you only need the positive value. So again, you can reduce your storage, your computational costs, everything by switching over to these real spherical harmonics, and you still retain all of this, the accuracy properties of the complex ones. In the radial dimension, I use the finite element method to discretize the equations. In the finite element method, you have basis functions that are only supported in local elements. And in that way, you approximate the solution in an element-wise fashion using this method. And it allows you to vary the basis polynomials in each element, so you can achieve both H and P refinement, which allows you to capture the solution quickly and accurately using minimal or using fewer degrees of freedom. In Poseidon, we use the Lagrange polynomials for our basis functions. Generally, we restrict ourselves to the first and second order Lagrange polynomials, but Poseidon is flexible to go up to any degree polynomial that you'd like, although if you go too far, you do incur numerical precision issues. But so that's generally why we stick to first and second order. They achieve the accuracy we need without suffering any potential numerical problems. Poseidon uses the continuous version of the finite element method, as opposed to the discontinuous version that a lot of people use. We do this because the gravitational field is supposed to be smooth. It is guaranteed, or we want it to guarantee that it is smooth, and this method guarantees C1 continuity of the solution throughout the domain by matching the basis functions at element edges, so you create a continuous approximation of the solution throughout the domain. With these choice of basis functions, the linear system is discretized, and it's sparse and it's diagonal, similar to what Nils showed in his presentation. We currently invert those systems using just a LAPACK call. At the moment, we are investigating ways of distributing this linear solve for when we have the problem split over a distributed memory system. So right now we're looking, we use LAPACK and scale LAPACK calls at the moment, but we're looking into improving that to make it more accessible to larger systems. One thing I mentioned earlier is with the conformal factor and the lapse function equations, those are nonlinear. So we had to come up with a way to solve those nonlinear equations. We chose to go with the fixed point iteration method, which is simple. You fix the right-hand side, you make a guess, and you fix the right-hand side by using that guess, and then invert the system to solve for the next guess. And you repeat this process until your solution has converged to some criteria, or you reach some maximum iteration. You don't want it to go forever. Now, the fixed point method is robust. It will go to a solution, as long as you start with a sufficiently good guess, but it does tend to converge slowly. So we decided to speed this up using Anderson acceleration. Anderson acceleration uses information from previous fixed point iterations to improve the next guess. And you tell the method by means of a memory parameter how many previous iterations to use when updating the current guess. And here you can see kind of the effect on changing the memory parameter for one test. m=1 is fixed point iteration without any acceleration. So this is your baseline, m=1, and you can see it takes a long time to achieve, comparable accuracy. Whereas as soon as you start to include information about previous iterations, you see a rapid decrease in the number of necessary iterations to achieve the accuracy you wish, which is very important when you're solving large, complicated systems. You don't want to do this multiple times. So Anderson acceleration was the way to go and what we use to improve the efficiency of the solve. Here we're starting to a few basic results. The conformal factor equation that we saw earlier has two terms on the right-hand side, one that is proportional to this energy density here, and another that is proportional to the extrinsic curvature, the approximate extrinsic curvature tensor. If you set the velocity to 0, then that extrinsic curvature tensor disappears, and you can simplify your system down so that you can solve something simpler like this. And that's what we did. We constructed a test problem with 0 velocity and a given energy density and solved it using Poseidon with a known solution. That way we could see how well the code it converges to the correct answer. Whoop, too far. Spoiler alert. So here we can see the red line shows the error convergence for first-degree polynomials. This is a 1D test, so this is really just testing the finite element method. The Lagrange polynomials are not the Lagrange, but the spherical harmonics do not come into play in this test. So this is just testing the finite element method. And you can see with the linear polynomials, we have excellent convergence rate. The black solid line is the reference is the ideal convergence rate for a first degree polynomial. You see we match that beautifully. Here, the dashed is the ideal rate for quadratic polynomials. And you see we have, excellent agreement with that. So the method is showing excellent agreement with, the error convergence that we expect. Next, we spin up the problem and we do a little bit of multi-D. In this, we have a homogeneous ellipsoid, also known as a Maclaurin spheroid. It is highly compact. This is crazy density, very small. It's basically a neutron star frisbee is what we've got here. And we calculate the conformal factor and lapse function around this neutron star frisbee. The Maclaurin spheroid has an analytical solution for which we can compare our results. And that's what we did. And we plotted the errors here in these two plots. Now, what's different about these two plots is this shows the effects of mesh refinement. The center one here is using a uniform grid, and you can see we have over 1,000 radial elements and to achieve a given accuracy. Whereas with mesh refinement, where we're refining just in the core, I believe with this one, we refine all elements within a radius given by the semi-major axis, and then we further refine all elements within the semi-minor axis. So you have a high concentration of elements here in the core of this problem, and very low resolution, outside. And given that decomposition.
Sorry to interrupt. You have about a minute left. That's okay.
Okay, cool. I'm almost done. Thanks. So given, these two completely different domain decompositions, we see very similar accuracy. Last thing is, like I mentioned, Poseidon has been coupled with Tornado, and we're doing adiabatic collapse runs. And here I give some solution or some of the results from recent runs with AMRX and adaptivity. You can see you know, the lapse function, the conformal factor, and the shift vector down here become stronger as things go on. You know, and that's what we're solving for, these two bottom panels, given this source in the top. And the last thing I guess I'm going to end on, if I've got the time, is I have a movie from and this is with Thornado. This is with an adiabatic collapse, the density profile, and we are using adaptive mesh refinement. And these lines are where the code is actually refining our domain. And it's kind of hard to see in this video, but you can see them dance around. We start with 2, and by the end, you know, we have several. So Poseidon is designed to do collapse profiles like this with AMRX, and you know, to return the metric. And that's, you know, what I have done is develop this code and help couple it with Thornado. So that's all I've got.
Awesome. Thanks, Nick. That's a great talk.
I like this
Does anyone
picture.
have- anyone have 1 or 2 quick questions for Nick before we launch into open discussion?
Yeah, if anybody's got anything.
Not, I have several.
I've got a quick one.
Okay.
Yeah, go for it.
Nick, you use Anderson acceleration. Big fan. It looks like having one additional iteration, you know, including x n minus 1, does most of the work. Would you agree with that?
Yeah. For our problems, just including just one previous iteration was enough to see significant improvement. You can see how the line kinks. There's no difference in the first iteration because there's no previous. And then in the second one, they all agree except for the one off. But after that, once you get up to 3, we didn't see much improvement after 3. I ran it on a couple of different problems, and sometimes you would see notable improvement between 2 and 3, but generally not much farther than that. You only really needed a handful of them to see, you know, this kind of improvement, in my experience.
Mine too, for different problems though.
Cool. No, yeah. No, it's great. It's easy enough to implement, and it really does, you know, show some improvements.
How do you
Can I follow up on this? Oh yeah, sorry, go ahead.
how do you do the optimization? What do you use for that?
So, optimizing what?
Good. In the Anderson acceleration, you have to do like a least squares optimization or something to get the weights.
Oh yeah. I want to say that's a LPAC call.
Okay.
Yeah. I mean, why reinvent the wheel? They do it very well.
Yeah.
And everybody has it, so. Any other questions? I see a hand.
Yeah, it's like Benjamin has a question.
So yeah, that was very interesting. I was curious whether I don't know if Tornado uses the same. Do you use the same grid for or the same set of basis functions for the hydro as you're using for the elliptic sol? And if not, how do you translate or remap the right hand side and the potential?
All right, no, that's a good question. So, and Sam can step in here and correct me if I speak amiss. But Thornado uses full DG finite element method in all 3 spatial dimensions. So there is, you know, there's kind of a disconnect in the basis function between Poseidon and Thornado in that respect, but we haven't seen any issue with it, and I don't think there really is an issue with it. What happens is Thornado provides Poseidon with the source values, the energy density, the momentum density, and then there's another S term that's a little involved to get it. But anyways, it hands all of these to Poseidon as nodal values within the element. It just, you know, it hands me that data. And when it arrives in Poseidon, there's a interpolation in the radial dimension to match Poseidon's not quadrant, but interpolation nodes. So with the continuous finite element method, the interpolation nodes include include the cell edges. It's including the cell edges is what helps, and your choice of basis functions, what ensures that continuity. With the DG method, you don't require that, but you also have to do extra work to make sure all the numbers line up across these discontinuities. So when the data comes into Poseidon, there's a linear interpolation of the source from their points, which are usually entirely within the element, to my points, which include the element edges. But since they're using the DG method, approximate or representing their solutions in my points is very straightforward and doesn't suffer any real loss of accuracy. In the angular dimension, I don't need to remap anything because the spherical harmonics are global functions, and I just evaluate, these global functions at whatever point, whatever angular point the source is located at. I hope that answers the question.
Yeah, thanks.
Great. Niels, you have your hand up.
Yeah, this was really interesting hearing about your numerical methods for a similar problem. I have a lot of lots of questions about the numerical methods and such. But what I really wanted to ask is, do you understand can you quantify what error this conformally flat condition makes? Well, on the physics side of things, right? Because for context, in GR, a spinning chaos solution has no conformally flat slices. We know that, and so when we simulate black holes, we have to discard the conformally flat condition to simulate black holes with high spins. We have to go to a non-conformal flatness, and specifically what we do is for binaries we superpose chaos solutions as the conformal background on which we solve for the conformal factor. And so for supernovae, I have no idea how this compares. Can you get away with conformal flatness even for spinning stars and
I get
or what error is being made here? Yeah.
Let's see.
How severe is this approximation?
Oops. Yes. So I'm just thinking of exactly where to start the answer. So for the extended conformally flat condition, they make this final approximation down here on the extrinsic curvature tensor. And the portion that they're dropping out, the approximation here, it's the transverse traceless portion of the extrinsic curvature tensor. When that's dropped, let me start that sentence again. You lose accuracy for highly rotating stars when you drop that term. The XCFC formulation, I think, was originally proposed by Cordero Carrion, and in their paper they show the effects of dropping making this final approximation. And as long as your star isn't spinning very fast, the term they're dropping remains very small. But as you spin it up, it becomes larger and larger. And so that's where you get the error. And so in their paper, there's a section where they try to quantify kind of how fast you can spin a star before you really start seeing deviations and results. For core collapse supernovae, a lot of them are simulated with little to no spins. I know a big area that's becoming more and more popular with core collapse is magnetohydrodynamics, where you do have rapidly rotating stars, and all of that spinning material, is what creates the magnetic fields. In those, XCFC is not a very good approximation, because you do have all that rotation. So this is the XCFC is good for mostly non-rotating, just straight in collapse kind of systems. It's exact in spherical symmetry is one of the benefits of it. But as you go up, you do start sacrificing things, and once you go up and introduce angular dependency, you lose, you're stepping away from exactness, and that rotation breaks it even harder.
Yeah, thank you. Could you point me to this paper that you mentioned?
Oh, yeah, sure.
Thanks. Doesn't have to be now.
Yeah, I'll find a link to it and I can get it to you, and I'll drop it in the chat as soon as I can. So yeah, I'll find a way to get it to you.
Thanks.
Mm-hmm.
We have about 2 minutes left. I do want to ask Nils a quick question.
Oops.
So Nick talked about how they enforce the continuity of the metric fields with their method, and you mentioned that you use DG methods, I think all the time. So I was wondering, how do you enforce continuity of the metric fields, and if not, do you think that induces any errors in your calculations?
Yeah, this is a really good question, and yes, it's something I noticed too when Nick talked about this. This is not a problem at all. So let's see. One important aspect is first parallelization, right? So using a DG method enables a lot of the parallelization. So in that sense, this is very helpful, because you can, with the DG method, you can move your elements to different cores, and then they only communicate over their shared faces, where each side of the element can have a different value, and then they communicate these values and compute numerical fluxes on the boundaries. So DG enables a lot of the parallelization. But then this discontinuity is not actually a problem for the solutions, because it converges away with resolution. So the discontinuity is only as large as your numerical error, as your truncation error, right? So it isn't any larger than any other error you make while taking numerical derivatives or anything like this. And therefore, also DG solutions are continuous to numerical error. So yeah, it's not a problem. The issue, this one sort of disadvantage DG has is that you have duplicate grid points on the shared element boundaries. Both elements have a grid point on there, and so this means you inflate the number of grid points that you solve for by some possibly significant fraction if you have the low order scheme. So this means you sort of balance the consideration here is how much you balance parallelization with inflating the grid points by having these duplicate ones on the shared boundaries. But parallelization always wins. So.
Yeah, sure. Okay, great, thank you. So it is noon. I think we ran over. That's my fault for talking too much. But yeah, thanks to both the speakers again. And if anyone has questions, I'm sure speakers are happy to answer, maybe over Slack or email or something. I'm happy to put you all in contact if that's needed. And so yeah, thanks everyone for coming, and hope to see you next month for another edition of VAST.
Yeah.
Thank you. Yeah, this was fun.
Yeah, thanks very much. And Nick, I would like to add your software to the astrophysics source code library. So
Yeah, sure.
yeah, just so I'll reach out to you, because I need like 3 sentences about it.
Okay.
So a good description. I looked at the GitHub repo, and the README is very short.
It's still a work in progress. Yes.
Yeah. Okay. So, okay, great. Thank you.
And Niels, I don't know if
Okay.
you saw, but Nick put a link to the paper in the Zoom chat.
Yeah. Yeah,
Yeah,
I dropped
thanks.
the paper there, and I can email it to you if you lose it.
Oh no, this link is good.
Awesome.
This
Cool.
will work. All right. Thanks so much.
You know.
See ya.